didn't get to watch you play Kahoot. All right, welcome to everyone else. We've just had a quick game of Kahoot, and here we go with a bit more of current electricity. I've left all these things at the beginning of the slides again, just because they're really important to know. And if you don't know them, that's a fantastic bit of revision to be doing. Okay. Now, the first thing I'm going to talk about is power. We talked a little bit about power in the slides last time, but less so in the actual webinar. So I'm going to talk about it a little bit more right now. So there's the equation for power, and power is measured in watts. And power is actually, by definition, the rate of energy transfer. So we've got energy divided in joules divided by the time it took in seconds. So let's have a little look at an example of what that would actually look like. So here's a practice question. Now, I suggested that you might want to do these last time if you wanted to practice them. And I found out that there was a little bit of difficulty for a few people in doing those. So if you've got a piece of paper to hand, just write down at the top of your piece of paper now, 450 newtons and then 0.2 meters, because those are our two measurements up there. Okay, because I'm going to change my screen so that I can show you how I would do that. So just change that and then change that to this camera here. Okay, so here's my whiteboard. Now, they said that a force or a weight of 450 newtons was lifted through 0.2 meters. Now, the first thing that I need to know for this, to be able to work out this question, it said, what was the work done? And I would need to know that work done is force times distance. That's an equation that hopefully you've revised. Okay. So this starts off as something reasonably simple, because now I've got work done is force times distance, and I've got a distance and I've got a force. And just to make sure that you're awake and you're actually doing what we were hoping, which is doing those. So what is the answer to that? I've just popped that up as a poll for you. Obviously, you can use your phone as calculators. You've got a calculator to hand. Good. There come people are actually voting. We've got a few in. Excellent. This is all going beautifully so far. Fantastic. So we can move on to the next step of this question. Brilliant. I'm going to give it a couple of seconds. I can tell that people are still doing this, but pretty much it's gone absolutely fine. We'll just end it there. And the vast majority of you got that was 90. And my question to you is, of course, 90 what? Because we're not, let's go back to this. There we go. So what we've just done is, how much work do they do? So we've got 90, and that was 90 joules, because work done is energy transferred. So it's measured in joules. They do this 10 times. How much work is done? Okay, so that's a nice simple calculation. We've got 90 times 10, and that gives us 900 joules of work is done. So now we have the next question. Now we're using our power equation. And remember, you might want to write this down. Power is equal to energy divided by time. So if you've written that down, I can swap cameras again and have a little look at what I've been writing down as I did that. So there was our 90 joules from before. So now they did that 10 times. They stepped up 10 times. So they transferred 900 joules. So we have energy is 900 joules. And they said that that was 8 seconds. Again, just to make sure that you're actually awake and taking part. This is going to get slightly more difficult as we go on. So what is the power? And I'll give you a moment to do that. And then what would be really useful as well is in the Q&A box is if you just want to type in the units that go after that. And let's just see those people that are finished, what goes into, if you just in the Q&A box, just tell me what you think the units of that are. brilliant. I've got fantastic. So I'm going to stop that at 30. How many? Nearly half of you done. Fantastic. Good work. Those of you that have done that, I'll just let you get it right. So the vast majority, if you got that right, and it was 112.5. And the reason it was 112.5 is that 90 divided by 8, if you put that into your calculator, was 112.5. What? Huh? Do you see the pun? I can see some of you, I can tell some of you are groaning, particularly those that I teach. The units were either, you could put a capital W, or people have written watts, because those are the units of power. Excellent. Okay, so we're doing okay so far. So let's move back to the slides, and I'll start going through a little bit more now, hopefully. Right, so now we've got the next question. Now this question is a little bit more complicated, but I would like you to try this question. So we've got a problem here. We have a problem. Now we have got a mass being lifted 1.5 meters by a weightlifter in 0.5 seconds. What is their power? Now, what I'm going to suggest is that if you think you can do that question, if you want to pop the answer in the Q&A box, and in a second, I am going to demonstrate how that question would work for those people that aren't sure. It's the 30 kilograms not being newtons that's the problem. Everything else in there then makes it comparatively simple. But actually, we have to use 3 different equations to do this. I'm just seeing if anyone is going to pop anything in the Q&A box. Let me just write down this 30 kilograms, 1.5 meters, 0.5 seconds. So because I'm going to switch cameras, I've just written this down and then I'm going to put it on the other camera. So I'm not sure how people are doing there. So they said weightlifter lifts 30 kilograms through 1.5 meters in 0.5 seconds. What is their power? Well, the first thing that I spotted was that this isn't a force. And before I used work done equals force times distance. Okay. And I've got a distance, but I don't have a force. Well, I can have, because the other thing that I know is that weight is equal to mass times gravitational field strength. And gravitational field strength, unless I'm told otherwise, is 10. Okay. So this is another equation that you have to know. Okay. You have to know these equations. So that then gives me 30 times 10 equals 300. So now that's 300 joules because it's work done. So now I've got an amount of energy. Okay. So, oh, no, I haven't. I've worked out my force. I've got 300 newtons. I'm drifting off there. 300 newtons. Gravitational field strength is 9.8, but you are allowed to take it as 10 unless you are told otherwise in the question. Okay, you are allowed to use 10 unless told otherwise in the question. So now that I've got 300 newtons, I now have a distance of 1.5, and then which would allow me to work out my energy in joules, and I then have a time of 0.5. So I've got 300 newtons times 1.5 is going to give me energy, and then I have energy divided by 0.5. So hopefully now you could use 9.8. Yes, that would not be marked incorrect, but for the purposes of this, to make it doable for people, quickly try using 10. So there you go. So what is the answer? Fantastic. Lots of people have worked it out already. That's absolutely brilliant. So I'm wanting you to carry on and do that. So I've worked out from this, the first thing I did was use this to work out weight, which is a force. So that gave me 300. I substituted that in there and multiplied it by 1.5. So I need that number. And then I used power is equal to energy over time to work out the final answer. A lot of you have worked out is, I'm going to end it there, is 900. So that was just an example of one of the questions that I had suggested that people try last week, that very few people tried, and I wasn't sure if that was because they weren't able to do it, or they just didn't fancy it. So I thought I would give you an example of how I would do that. Right, hang on, let me just get this working again. Right, explanation time coming up. So I'm going to stop asking you questions for a little while and just do some explanation. So this is the bit where you just watch what's on the screen and listen. I'm not going to make you do any more calculations in the immediate future. The required practical. It's really important that you learn the resistance of a wire required practical. The best way to do that, if I just flick forward a slide, hopefully, here is the freesciencelessons.com video on the resistance of a wire. Also on BBC Bitesize, there's a really nice method. The thing is, the method changes a little bit depending on how you look at it. So you've just got to know the general method. The common question that you get asked is, how would you find how the length of a wire affected the resistance of a wire? It is absolutely fine to draw a diagram and say set up the equipment like that, rather than take an ammeter, connect it in series with a resistant board and a switch, make sure you have a voltmeter in parallel, make sure that's connected to the lead in the crocodile clip. You could draw that diagram labeled and say set up as in the diagram. That's fine. But what's really important here is that we talk about what we're actually doing. So what we're doing is, this resistance board generally has a meter ruler on it. So it's very easy to get the crocodile clip and measure out 10 centimeters, 20 centimeters, 40 centimeters, however long you like, of wire. Okay. Things that are important to remember. It's very important to only turn the power pack on, take the values of current and potential difference, record them and turn it off again quickly, because the wire gets hot. And temperature also affects the resistance of a wire, and that would make our results invalid. So we have to do it quickly. For each one, we are going to need to take 3 readings to make it more accurate, and also to remove any anomalous results. So you need to make sure that you mention things like that, rather than just the simplistic method. Rather than just saying, were you to be asked this question as a 6-mark question and it's a common one, you need to make sure that you say, and then I will calculate the average current of my 3 values. I will calculate the average potential difference of my 3 voltages, and I will use V equals IR to calculate my resistance. You could then plot a graph of resistance of the wire against length, and you would be able to talk about any relationship that there was between those 2 things. That would be a nice, clear method. Sometimes in the question, they say, how would a student use this equipment? And then they have done much more of it for you. The other thing that has to be the same is, you obviously have to use the same piece of wire each time. That's very important. If you change the wire, you might be changing the thickness as well as the length. I'm going to give you a clue now. The 6 marker for this week is about being able to write a clear, concise and valid method for this. To get all of the marks, you must talk about making it valid, about what you're going to measure, what you're going to keep the same, how you're going to calculate it, and what graph you're going to plot. A really good way to test yourself on this is to have a look at this, watch that video, read BBC Bitesize, and then without anything in front of you, answer that 6 marker. And then obviously when all of your teachers mark it, we're going to be able to see whether you've got how you construct it. People get really bogged down in the tiny details of the method. What matters is that what you have presented will actually be able to measure what you want to, which is, does the resistance change as the length changes? You must be controlling everything that needs controlled, the temperature, the thickness of the wire. You must be taking repeat readings and explaining why, and you must be saying how you're calculating resistance, rather than just calculate resistance. You need to be very clear about the graph you're going to be plotting, what's your Y and what's your X axes. Okay, so that's a 6 marker, and that's something that I think it's really important to know how to do. So that's why I've put that there. So that's enough on current electricity for now. We've looked at series and parallel circuits. We've looked at components. We've looked at some of the equations. We've tried a couple of calculations there. So let's talk about mains electricity. Now, I'm not going to talk about everything in mains electricity, but a lot of people leave it out because it's sort of comparatively simple. But let's just have a look at some of the key things that are in there. Okay, so mains electricity, we've all got alternating current, AC current, alternating current. You need to know that AC stands for alternating current. DC is direct current. That's what we get from cells and batteries. Plugs, mains current, AC, alternating current. And alternating current in this country, it's 230 volts. That's the potential difference that we're getting out of our plugs. It alternates at 50 hertz. That means it changes direction 50 times per second. Now, the bit that's not up there that I thought was, and 13 amps. That's the most current that you're going to be able to draw out of a mains plug in the UK. Okay, so that's what an oscilloscope trace, and an oscilloscope is something that allows us to see the current, the potential difference and the changes in direction. And that is what that would look like. Sometimes they give you an oscilloscope trace and ask you what is the potential difference, and you just read off here, or they give you the time along the bottom and ask you what the frequency is, and you look for the number of changes per second. Okay, it's an oscilloscope screen. You just need to recognize that word. So this allows us to look at waveforms, for example, from sounds, and it also allows us to see alternating current, if you like, as a visual representation of it for us. Okay, but there's a few things that are a bit simpler than that. So the main thing is knowing about a plug. Now, certainly my experience of teaching students that are higher, oh yeah, plugs, that's really easy. The thing is, you've got to actually understand a few things about plugs as well as just knowing it. So we've got a live wire and a neutral wire, and I've done the colors there. So brown, live wire, neutral wire is blue. Okay, the current through the appliance alternates because it provides an alternating PD between the two wires. The neutral wire is earthed at the local substation. So the neutral wire has got an earth, okay, where the electricity is coming to the building, but the live wire is the dangerous one because its voltage or potential difference constantly changes from a positive 300, okay, to a minus 300 in each direction, okay. And that is what the wire that you could get an electric shock from. And the reason is there is no earth, there is nowhere else for that current to go. And if you get hold of just that wire, it will run out down through your body, giving you an electric shock, which is obviously unpleasant. Those people that I've taught before, ask someone else about the story of David. Hope I just made someone smile. Right. Sketch a plug and label it. You need to know where these different things are, but slightly more than that, you also need to know what they are for. So we've got the live wire. We've just mentioned that. That's the one where you've got the alternating, okay, potential difference voltage going backwards and forwards in two different directions. We've got the neutral wire, okay, which is earthed at the substation, and the earth wire is a safety device. We only really find that in electrical devices that have got a metal case, because what that does is if there's a problem inside and the wire touches the metal case, instead of it electrocuting you, the electricity runs out through the earth wire down to earth, down to the ground, and prevents you from getting electrocuted. The reason these pins are made out of brass or copper is that that is an absolutely superb conductor, and that's really important. The reason that they are covered in plastic is that that is a really good insulator, and that protects you. The plugs generally are made of plastic because that is tough, durable, and an insulator and doesn't conduct electricity. The cable grip is there for safety. It stops us pulling the wires out. And the fuse we're going to talk about in a minute, but fuses are devices to protect the electrical appliances from receiving too much current and potentially catching fire or being dangerous or harming us. Okay, so there's some quick questions. Again, you are not on the slides expected to answer these questions. They are there for you to test yourself. If you have a look at that and you're doing some revision, well, can you now answer all of those questions? Because if you can, then you know everything you need to know about a plug and you can move on and you've done it. If you don't, you need to go back, listen to what I just said and see if you can do it next time, because then you would know everything that you need to know about a plug. And there are some questions there about spotting. Now, this is a common style of question, which is spot the mistake in the plug. So the cable grip is not done up, which means the cable could pull out and that would be dangerous. The wires could touch each other. And the earth wire isn't connected, which means that in the case of there being a problem, the appliance could potentially electrocute you. Here's what I spoke about earlier on the oscilloscope's trace, and you being given oscilloscope diagrams and asked to work out the questions, work out the values. Now, I've given these ones here. Again, you don't have to do these questions, but if you look at that and think, I'm sorry, I don't have a clue what he's talking about, have a really careful look at that and see if that helps you work it out. Okay. Right. Here's the bit that I want to spend slightly more time talking about: power and fuses. So there is the equation triangle for power. So power is equal to potential difference times current, okay, V times I. And power, we've already said, is measured in watts. So we had a different equation for power a moment ago. We had power is energy divided by time. It's still the rate of doing work. It's still joules per second, but in an electrical circuit, that's how we calculate it. It's still the rate of energy transfer. That doesn't change. It's still measured in watts. So we've got potential difference in volts and current in amps. Now, we can use this to work out what fuse we need. The reason we can do that is a fuse needs to, we say a fuse blows, but what a fuse actually is it's a little tube with a really thin pieces of wire inside. And when too much current flows, that wire melts and breaks the circuit, and that prevents any damage from happening. Too much current flowing through your body, you getting electrocuted, that stopped. Too much current flowing to the metal around the outside or the components inside and catching fire, that isn't allowed to happen either. So the fuse rating always has to be the fuse rating above the amount of current it actually needs. Fuses in this country tend to come in three types: 3 amp, 5 amp, or 13 amp fuse. And you put the fuse that is above the amount of current that is needed. And if it gets to that, that wouldn't work. So let's just have a quick look at an example of what that would look like. Okay, and then I'm going to get you to work out a couple yourselves. Okay, so shall I just stop sharing so you can actually see that? So we just said power, is equal to V times I there. And I very foolishly didn't look at my values. 700, and so my power rating was 720. Whoop. My power rating was 720 and my voltage was 230. Right, let's go back to where I was. Okay, so I've got 720 is equal to 230 times I. I want to know what I is, so I've got 720 divided by 230. I do make sure that I do that on a calculator. So I've got 720 divided by 230, and that says 3.13. Now, this is the bit that's really important. 3.13 amps. Okay, 3.13 amps. So if I then just go back to what we were looking at just there, 3.13, it needs 3.13. Which fuse am I going to choose? I'm going to have to choose a 5 amp fuse. And this is where people often go wrong. Go, oh, well, it's almost 3. I'll pick a 3. That's no good. Normal functioning of that toaster requires 3.1 amps. So the 3 amp fuse will blow the second you turn it on every single time. But if 5 amps tries to flow through the toaster, which is too much, but not so much that your toaster is going to burst into flames, then it will fuse. And there's a problem if that happens, because that isn't the normal expectation. Okay. So hopefully a second ago, you got to write that triangle or equation down. So I'd like you to do that now if you haven't. P equals VI, or write the triangle down like that. And then I'm going to just test you on a couple of these questions here. Okay. So what I'm going to do is make sure that you can remember about a plug, and then we're just going to try a few of these questions to make sure that you can do them. So I think that's probably enough now. So where's my polls gone? Ah, there we go. Right. So let's start with the first one. What number do I need? I need number 18. Right, here we go. First of all, really quickly, what's the yellow and green wire in a plug? Can you remember that from just seconds ago? Just make sure you're awake. While you're doing that, I'm going to change camera if I can. Excellent. Back to me. Right, I'm going to call that there. Not quite all of you. So most of the people who responded knew that it was an earth wire. Not everyone does. Really important. That's a nice, easy piece of revision. So the revision task today is about knowing all of those things, and I'll show you that at the end. But if you don't know all of these things, you need to do that first before you do any of the other things. And if you run out of time after that, well, you run out of time. Just share some evidence with your teacher, and that will be fine. So now let's try some of these calculations here. So let me just get this back up so that you can see it nice and clearly. Okay, so now we're going to look at what fuse does the electric fire need. So we're talking about a bar fire there. What fuse does that actually need? So I'm going to put up some possible answers, and you are going to have, let me move it down there. You're going to decide which fuse it is that actually needs. What fuse would a fire need? I have a feeling that there's a little bit of guessing going on as opposed to working it out. Only a quarter of you so far have come up with an answer. Just give you a little bit longer. Remember, P equals VI, which means you can work out the current needed, and you have to choose a fuse that is bigger than that number. You have to choose a fuse that is bigger than that number. Right. I'm going to stop it because that's been running for a minute. I'm going to explain why. About 60% if you got the right answer. So it was a 13 amp fuse. Now, the reason for that is this. To work out the current using our triangle, power divided by potential difference, or the volts that we've got, gave us 8.69 amps, 8.7 amps. So the only fuse that we could possibly choose that's bigger than that is 13 amps. Is 13 amps. So let's try the next one. Let's see if that helps you, that explanation. What about the hairdryer? Obviously, I know a lot about hairdryers. Which fuse are you going to need for the hairdryer? Some people can see what the answer is going to be there because of the size of those numbers. I still think some of you are doing random guessing rather than actually working it out. We can work out the current by dividing power by the potential difference or the voltage. And that is going to give you an answer of more people have voted this time though. So, and more people are correct. So I think you're following the advice this time. I'm going to end it at the same length of time, 45 seconds. There we go. Share the results. And the majority of you got it right this time. It's 3 amps, because if we divide 300 by 230, we get 1.3. So it only needs to be a 3 amp fuse. Fantastic. Right. Not very long to go. Let's move forwards a little bit. So this question was in last week's questionnaire and slides, and it was one that people kind of missed out. And so I wanted to explain it again, but really, I think I'm going to because I'm aware we're running out of time, this is about the live wire and the fact that the live wire is the one that has no earth to it. The only way out for the electrical current is through his body if he touches it, and therefore he will get an electric shock as the current runs down to ground. Okay. Again, these are questions that were in there last time, but not everyone had to go out. They're there for you to practice if you are now more sure than you were before. So here is the first of the 4-mark questions that I want you to answer. Now, I don't want you to just spend a couple of minutes just throwing down any old answer. You've just had a webinar and you've got some slides that really explain what earth wires and fuses are for, and therefore you should be able to give a perfect answer. Take your time, have a think about what goes in it. Okay. The other thing that's here for you to do is this. Now, can you make a single diagram that shows that you know what all of the wire, the colors of the plug are for, what the fuse is for, common faults with a plug, what's a circuit breaker that I didn't mention, look that up. Well, how does a fuse work? What are they for? How you've just calculated some fuse ratings. What's AC DC? Not the 1970s heavy metal band, but in terms of electricity, and to be able to talk about all of those things. Knowing what's on there is much more important than the 6-marker that is also attached in your Google Classrooms for you to try. Okay, so I'm just going to stop sharing that. We have got, is this all the work set for next Wednesday? Yes. So what you have got to do is you have got a 6-marker and a 4-marker. You've got that revision task and you've got the Google quiz. If you are unsure about any of the earlier questions, you've also got questions to practice as well. And if you do the revision task, we want uploaded evidence that that's actually what you've done. I think if you do all of this properly, if you take your time over the 6-marker and the 4-marker, you do that revision in a great deal of detail and you do the revision quiz properly, that's going to take you well over an hour to do on top of having watched this webinar. Okay. Now I did have, if we have got time, I did have another quick, no, that's not the one. I've got another quick Kahoot for you. That's actually just going to test you on some of your equations. So this is the other thing that you really need to know are your equations. So again, people saying, is that all I have to do? The thing is, if you do this and you don't actually know these equations, you have to go away and learn them. Again, not exactly sure what our assessments are going to look like, but we are having assessments and these are a core part of P1, absolutely core part of P1. So in the 5 minutes that are left, if you join, I'm going to test you on these and you can prove or disprove that you know exactly what is what for these. Let me just find my share screen. Where's it gone? Where's Zoom gone? Oh, there I am. Fantastic. Right, hopefully you can now see that. So I'm going to stop recording at this point because people don't need to see us see if